I had a request to talk about one of the graphs I showed in lecture 24. And before I show that actual graph, let's just draw a simple version of that graph before we unpack that more complicated one. So in lecture 24, we talked about allosteric enzymes. And allosteric enzymes have the ability to get regulated by some modulator. So if this is the active site where the substrate would come in, there's a separate regulatory site. If you're a heterotropic modulator, then you'd work on this other site. You could also, there are some cases where the regulator is going to bind the active site. The substrate is a regulator. And then you're talking about homotropic modulation. But either way, you have the change in activity for an enzyme being regulated by a ligand. But this is different from the inhibition we talked about in a previous lecture, because these enzymes don't follow Michaelis-Menten kinetics. So if you draw a Michaelis-Menten graph where you have substrate concentration on the x-axis and initial velocity on the other axis, remember Michaelis-Menten kinetics for an enzyme, the line would look hyperbolic. That's not the case for allosteric enzymes. So allosteric enzymes are often multi-subunit, and they show kinetics that's sigmoidal. This is really reminiscent, and that's kind of ugly. Let me fix that little curve. This is really reminiscent of another relationship we looked at earlier in the quarter, which is hemoglobin. And that's because the same concepts are coming into play. For an allosteric enzyme, you have a version that's high affinity. And I should say you might have several versions. If you have multiple subunits, then you'll have more lines. And we'll talk about that with the next graph. But then we're just talking broadly here. If we're talking about having two states, you could be high affinity or low affinity. And remember we talked about hemoglobin. It is low affinity, but then can switch to high affinity. So allosteric enzymes are the same, have this or showing the same concept. So that's that sigmoidal curve that represents the ability to shift between a low affinity state and a high affinity state. And because most allosteric enzymes have subunits, they're showing this kind of cooperativity. There's multiple active sites, multiple regulatory sites, and so you'll have allostery being shown where you have the binding of one molecule affects the binding of another molecule. So for an allosteric enzyme, you still look at its halfway point as something useful to acknowledge. Remember that halfway point of Km, substrate concentration at half maximum velocity. So you still have an approach to Vmax here, because this enzyme is going to have a maximum velocity. But instead of saying Km, because this isn't Michaelis-Menten kinetics, that substrate concentration at half maximum velocity has a different name. It is Ko.5. And so that is the substrate concentration at half Vmax. And so this may change as a result of a positive or negative modulator. So I took this image out of the textbook, and it's hard to generalize and say all allosteric enzymes will have a particular curve for their binding with whatever regulators they have, because some regulators do affect Vmax, others don't. Some allosteric subunits have, or sorry, allosteric enzymes have many, many subunits, some just have a few. But in general, they'll have multiple subunits, so you'll see cooperativity. And this graph is specifically for an enzyme that has multiple subunits, and that's, you can see that in the book, multiple subunits. So that means you've got multiple active sites and regulatory sites for both the positive and the negative modulators. So the original curve for the enzyme is the sigmoidal curve right here. And I mentioned specifically that neither of these positive nor negative modulators affect Vmax, so Vmax not affected. So you can see every single one of these lines on this graph approaches that Vmax. Even this bottom line right here, it will eventually get to Vmax. You can see it has a gentle slope upward. So let's just unpack this, all these curves one by one. So if you have a positive modulator, you're going to shift the curve to the left. And because there's multiple regulatory sites, the more ligand or more modulator that you add, the more you'll shift the curve to the left, and you'll lose that sigmoidal shape. You see that the K.5, which represents the substrate concentration at half maximum velocity, you can see that gets smaller and smaller with more and more positive modulator, because the positive modulator is making the enzyme more active. It's increasing affinity, and it's making it more active by giving it a higher affinity for the substrate. The more affinity you have for the substrate, the more quickly you can bind them. The more quickly you bind them, the more quickly you can turn them into product. So your K.5 will get smaller and smaller with higher and higher concentrations of positive modulator. Even if you didn't have even if you didn't have a lot of different subunits, you'd still see this shift to the left, because you're going to be making the enzyme more active, have a higher affinity for substrate. Now let's look at the other side. You could have a negative modulator, and what that does is that it lowers the affinity of that enzyme for its substrate, so the K.5 gets larger. You can see it goes in that direction as opposed to the other direction. So lower and lower affinity for the substrate means that you're going to have a less active enzyme. Less active enzyme, you're going to take you're going to take higher substrate concentrations to get to Vmax. And so those lines will be shifted to the right, and you also, in your shift, lose the sigmoidal shape of your curve. And you can see that you still have the sigmoidal shape a little bit if your shift is small away from either side. But if the shift is great, you lose that sigmoidal shape. So when you have a modulator creating you're creating a big switch to a high affinity state, you can get all the way to hyperbolic for your curve. Same thing with really tamping down the enzyme activity with a negative modulator. So hopefully this cleared some things up, and let me know if you have any further questions.